eu vou
sentar, né?
Você vai sentar, você vai sentar lá. Lá, não, tô brincando. Eu falando isso não grava, pelo amor de Deus, hein? No YouTube. Eu fazendo piada. Tá gravando, sempre sai ao vivo uma Daí você fala um oi quando começar, né? Pra não dar um... Boa tarde a todos, né? Essa daqui é a última apresentação do nosso ciclo de apresentações de professores de universidades internacionais que vêm nos visitar. Então, hoje temos a visita do professor Daniel Dias, da Universidade de Grenoble Alpes. Ele veio aqui por uma missão de um projeto CAPES-COFECUB, que ele tem, né, com o Departamento de Geotecnia da Escola. E o professor Daniel Dias tem grande experiência em modelagem numérica e, entre várias estruturas geotécnicas, ele mexe com essa parte de Energy Geostructures. E é um prazer recebê-lo aqui, né? Já esteve conosco no Brasil em outros trabalhos aí que ele sempre contribui com o nosso programa de geotecnia. E vou deixar vocês aqui com a apresentação do professor Daniel, com a sua vasta experiência. O currículo dele é só vocês procurarem no Google e vão ver o quanta coisa só ele já fez, né? Bem extenso. Professor Daniel, fique à vontade, né? O professor Daniel vai fazer a apresentação em inglês, tá? Ele compreende um pouco de português, as questões depois a gente vê como é que faz, se precisar, né? Daniel, thank you very much. You can start your presentation.
Ok. Se eu tivesse tido mais tempo, eu podia ter tentado fazer essa apresentação em português, só que para mim necessita muito mais tempo de fazer. Sim, para mim é muito mais tempo, muito mais energia fazer a apresentação em português que em inglês. Então vou então fazer em inglês. Depois, outra coisa, eu ainda venho bem cansado, quer dizer que eu poderia fazer melhor, de certeza, se eu não estivesse tão cansado. Okay?
O professor chegou hoje da França.
Cheguei de manhã. Okay, so let's start. So my name is Daniel Diaz. I'm working at the Grenoble University. So it's a French university. It's in this university we have one lab which is working on geomechanics. It's one of the two best labs in France for geomechanics, and the name of this lab is Soil, Solid Structures and Risks. So I'm more a geotechnical engineer, so I'm more involved in the soil part. Sometimes I'm involved a little bit on risks, but the presentation of today is more focused on geotechnics. So the topic is behavior of energy tunnels. So as I didn't know what was your level about geothermal energy, so I will begin by simple things, just to remind what is a geothermal energy, where you can find it, how it works, and then I will focus a little bit more on tunnels, on a more specific work like unsaturated soils, like one of your colleagues is, I know that one of your colleagues, I don't know your name, but he's also Mohamed. So Mohamed is also working on unsaturated soils. So let's deal a little bit about geothermal energy and what is geothermal energy and what is the goal of taking some energy from the soil. So what we know, it's commonly known, is the fact that at some depths, so at accessible depths, we have an increase with an average of 2.5 to 3 degrees every 100 meters. So it means that at the surface, we will have a variation of the temperature. In Brazil, not much, yeah, but in France, you know that now the temperature is more or less zero and probably will go down to -5, -10. And during summer, we will have more than 30 degrees at the surface. So the idea will be to go in a deeper place where the temperature will be more or less stable. And if it's stable, means that we will be able to take the energy from this deeper point. And if you have to cool during summer, if you have 36 degrees outside, you will be able to take the energy from the ground, which will be probably at a lower temperature. And in winter, it will be the contrary. Means that you will have -10, and in your soil, probably you will have something like 15. Some places, so we know that we have an increase of 2.5 to 3 degrees, and in other places can be higher. So it means that the efficiency of this technique should be first analyzed, designed, and means that in France, probably we will not have the same efficiency that you will have in Brazil, and probably you will also not have the same needs. In France, we will have to heat and to cool. Here, heating, not much, if I well understand. Yeah? Okay, so geothermal energy, people is using it since where is the pointer? Is there? Yeah. Since yeah, but it's not working on the screen. So it's people is using geothermal energy since the Paleolithic times. For the first thing is for bathing. When you want hot water, you will go for bathing. So it's a good idea. Also for in the ancient Roman times, and nowadays the idea is to try to take energy for electric power. For using deep geothermal systems. So I will not deal too much with deep geothermal systems, but the main idea of deep geothermal systems is the fact that they are deeper, and so the temperature will be higher. And then you can bring much more energy than at shallow surface. For tunnels, for all the geotechnical works, we will be at probably 50, 60 meters. Not much, okay, so in this case, we are more focused not on the electric. So for the deep we used to say that it's not really a closed loop. Why? Here you will inject, and here you will take the heat, but sometimes it's not really closed. Yeah, so it's what we say. It's more an open loop, and sometimes we have to do some fracturation also to be able to hear. If it's rock, we will have to create our Indians fracture system to be able to link, in fact, these two pipes. But at the beginning, they are not closed. They are an open loop. In the geothermal energy I will deal with, we focus on closed loops in all the cases. So, okay. So what we know also, so it's it's a slide from an Italian colleague. It's why it's all is written in Italian. But I know that some of you have also the heat depth. At depths higher than 10 meters, we will have more or less a constant temperature all the year. So it's very interesting. And at the surface, so for depths inferior to 6 meters, you see that we will have a big variation of the temperature. So the idea, if we want to have a good efficiency, is to try to have a structure which is deeper than 10 meters, something like that. Like that, you will always have a constant temperature, and you can take calories for heating or for cooling. Yeah? So it means that if you have very shallow structures at the surface, they will be the temperature of these structures will be modified by the surface temperature, and it will decrease a lot the efficiency of your geothermal system. So I already told you that we have the open systems. So these are, most of the time, they are not so efficient. And we have the closed systems, and you see that in the closed system, you have the input and the output tube which are connected. So it means that in most of the geotechnical structures, we will deal with this, the closed system with the heat pump. We will see the heat pump. So let's deal now with the energy geostructures. In geotechnics, we have more or less three kinds. We have the piles. So, what is important is the fact that if you have to do your structure, it's not very difficult to add some pipes inside. Yeah. In Paris, we have a lot of works now. We have the Grand Paris Express under construction. Grand Paris Express is a tunnel construction of more or less 200 kilometers. So it's a very long one. Plus, they are creating more or less 72 underground stations. So it means that we will create a lot of structures that can be linked with geothermal energy. But the main problem was the responsibility. In fact, they began, in some of the stations, they tried to set some tubes, but in France, I don't know to say in English, it's when you have to design, you have a people who will control, and as the guy who controls, they didn't have the experience of that, they say, no, I don't want, so they stop. Means that in some of the stations, they began to set the tubes, and they have to fill the tubes. Yeah. By the fact that the controller have no experience, so he says, no, I don't want to take the responsibility. So in France means that we have created 200 kilometers line plus 72 underground stations with no geothermal energy. So it's a pity for France, as all these lines are connected to Paris. Paris is at, sometimes they cross Paris, sometimes they are very close, so it's a real pity. Yeah. So it means that sometimes it's not possible, but it's not the fact that it's not interesting, it's more the other parts around which we do not permit that. So I was telling about the piles, so it's the first kind of, Christina is working a lot on piles, but we can also use another kind of energy geostructures, it's the parkings. So here you see the parking. What is interesting is the fact that one part of your parking, one part of the concrete wall will be connected to the soil, so you can take some calories. This is can be a good energy geostructure, but the problem is the fact that sometimes it's not so. Sometimes it's just 1 or 2 levels. One level more or less 3 meters, 2 levels 6 meters. So we didn't reach 10 meters to have a constant temperature. And the other thing is the fact that you will have inside some heating. So it means that you will reduce the efficiency of the system. Yeah? Remember, you should be more or less constant at that constant temperature to try to take the temperature. And another kind of underground structure is the tunnels. We will see that this is a big possibility, but we didn't have a lot in the world. So I will show you some cases. So here it's a case. I will show you again this case, but it's a case. So in Italy, so in Torino, one of our colleagues, so Professor Barla, he has done an experimentation on only two rings. Yeah. When you are excavating with a TBM, a tunneling, you will set some rings, and he just have the permission to set 2 rings, and he showed that it's working well. The big problem here, and it's more or less the same as the one with the controller, is the fact that so your tunnel, when you are doing a tunnel with a TBM, means that you will have at least 1 kilometer long. Or the TBM is something which will cost more than 10 to 20 million of euros. So you should have a long distance to excavate to be efficient. And then, yes, you will produce energy. So the guy who will design and we will build the tunnel, at the end, he will not be the owner of the tunnel. So who will take this energy, and did they have buildings to heat and cool or not? And it's the big problem also in France, by the fact that we have a separation between the guy who will do the work and nobody will take care of the energy. And it will not be the same guy who will create energy, generate energy, manage the energy, and it's never simple. But in all the cases, the tunnels probably are the future. Why? In most of the cases, they are excavated at 5 diameters. So the diameter of the tunnel is more or less 10 meters. We will excavate them at 5 diameters, so more or less 50 meters. And so means that we will be at the good level to obtain a constant temperature. The other thing is the fact that as you have a diameter of 10 meters, the surface is very important. Yeah? The surface, and you know that you have a length of at least 1 kilometer, so it means that it can bring a big amount of energy to the cities. Here, so I have other pictures, but you can see that it's not so complex. In fact, you will have to set some steel rebars to create the rings. So the ring for a tunnel created by a TBM, the ring has more or less 30 to 40 centimeters. So you have space for the steel rebars. So here you see the steel rebars. Plus, they should just add the tubes to allow the circulation of the fluids. So here another photo. So it's the case of the Torino. It was an experimental one, and what is more complex is the fact that the segment, the ring, it will be made of several segments. So they should connect each segment, and it's not so easy. So it means that, yes, we should, it's like, I don't know, like it's like the Apple, the pads. Some years ago, they didn't exist. Yeah. Now you can buy them. Here it's more or less the same. Here it's just an experimental, so it costs a long time to develop and implement. But if we decide to go ahead, they will be efficient. They will bring a lot of energy, and the cost of these things will reduce. Yeah. In this experimental thing, it was complex by the fact that they connect some normal rings with rings which were connected with rings with tubes. So it was not so easy to set up this in Torino. If we have a look around the world, there is not much energy tunnels. So the bigger ones are this one, so the Torino. But you remember that we have only 2 rings, but not much. In the Katzenberg tunnel, the Nanaori tunnel, the Sejam tunnel, the Lincheng tunnel in China, but only 1, and the laser. So the bigger ones are 5, 6, not much. Another kind of energy tunnels which can be used are the ones on the pipelines or the sewage systems. Means that yes, you can have fluids, and you can bring from the fluids, we can take some energy from the sewers. Sure that the efficiency will be lower by the fact that your sewers will be probably at 3 to 4 meters, but you can also bring some energy from these ones. Here another picture of what was done. So it is not extensive. You see that the PhD I have, he finished in 2020, so we have a lot of data till 2017. But what we can see is the fact that yes, we have most of the energy geostructures are piles. Here it's more or less 80%, and we have less than 100. Then we have a little bit energy walls, and the smaller part is energy tunnels. Means that we can develop a lot to try to bring much more energy to the cities. As the tunnels, in most of the cases, the tunnels are built in cities or connected to cities. Here it's a distribution with the countries, and you can see that yes, it's Great Britain where they have a lot of energy piles. They have also big standards. They have big recommendations. So it's easier also for the engineers as all is more regulated. In other countries, it's less regulated. Like in France, we have something which deals with, but it's more or less a copy of what was done in Great Britain. And the companies didn't have the habit to do that. So it's difficult to move and to change. So yeah, the good thing is also the fact that we will save a lot of CO2 with this kind of energy. You know that it's on the ground, so we just have to take it, in fact. Yeah. So it's not like we will have to take the coal, burn the coal, or for the oil. It's not the same. We can say that it's more or less a clean energy or a green energy, not like coal or other things. Okay, let's discuss. So it was an introduction for geothermal energy, geothermal structures, and energy tunnels. Let's deal now about what we have done, a small piece of what we have done in this PhD. So in all the cases, we will have to do a circulation of a fluid in the tubes. Yeah. We will set a fluid which is a lower temperature or higher. You will take the calories from the ground and then you will bring them to a heat pump. The heat pump is necessary, and we will have to give some energy to the heat pump to condensate the calories. Yeah, so it means that the heat pump on the system is probably the main part of the system. Yeah, it's very important. So the efficiency of the heat pump is also very important. I'm a geotechnical engineer, so I don't want to manage that. Yeah, so I suppose that a lot of other people will do better than me. So here I will focus only on this part and how the soil, how we will be able to take the calories from the soil. And then the idea, the heat pump then will be connected to, I don't know, structures to heat or to cool. You understand that. So I already deal about the piles. So the pile is the most common energy geostructure. So you have the diaphragm walls. The diaphragm walls can be installed from new diaphragm walls or can be also installed in older ones. If you have to renovate them, you can probably recreate a lining in front with some pipes. And the tunnels, we already dealt with the tunnels. We have two kinds of tunnels. So I will introduce a little bit with these two kinds. The first one is, I don't know if you have had a course about tunneling. No? You know the difference between tunneling and mechanized tunneling? Conventional and mechanized tunneling? I feel that I am tired. No? So this one is the conventional. The conventional tunneling, you can use normal machines, so means that it's trucks, the scrappers, yeah, classical machines. But in this case, the soil should have a cohesion. Means it should be stable by itself. Yeah, I will excavate, but I will excavate step by steps. And in this case, we used to say that it's a conventional tunneling. Means that we will set, yes, steel rebars, probably sprayed concrete, but at the face, the soil should be stable by itself. We can help a little bit the face by using steel bars inside or steel bars or fiberglass bars, but you should have some cohesion. If you have no cohesion, we will not be able to do conventional tunneling. Another big difference, so conventional tunneling, we can be used for smaller lengths. So if I have to deal with 100, 200 meters, yes, most of the cases I will do conventional tunneling. The only case where, the other big difference is the shape. You see that here, when you have an inverted U shape, means that it's conventional tunneling. Yeah, your truck should circulate, so you should have something plain. Yeah. In the case, the mechanized tunneling, it's a TBM. So the TBM, it's a machine which will rotate and will excavate, and most of the case, in France, in all the cases, it's a circular shape. In Japan, they can have other kind of shapes. In China also, they can have some strange shapes, yeah, so more complex shapes. It costs much more. In France, only circular. But in another big difference is the fact that in conventional tunneling, you have to excavate, and then you will set a temporary support, and behind, you will set the final lining. Yeah? So 2 steps. So it means that here, you can see that they have excavated, and before setting this concrete layer, which will have probably between 50 to 70 centimeters, they can set the tubes. So they have the temporary lining, and they set the tubes between the temporary lining, and then they will set a big shell of concrete to block all the system. Here, in this case, the TBM, it will do all. Means that you will excavate, it will protect behind you have a steel, it is made of steel, so it will block the movements, and behind the TBM is able to set the support. But it's not a temporary lining. The TBM will directly set the final support. So it's why, in this case, you should create your ring elements, and you should introduce them. You should introduce the tubes directly in the rings. So here what you can see, we have two big experiences for mechanized tunnel. So the one, the Enerton, it was the one for Torino. And you see that in this case, the tubes are perpendicular to the direction to the excavation direction. And here they are parallel. They were parallel. So this one was built before this one. So it was just in fact, it's very difficult to compare the efficiency, as it depends a lot on the depth, it depends a lot on the temperature, it depends a lot on your demands. At the surface, what is the difference of temperature? So here you have the same, more or less the same. And you see here what is interesting. You see this is a segment. So you see that they are composed of different segments. Here you should have a connection. Yeah. So you should prepare the connection and then finish the connection between the elements. This is not so easy to set up. This one I already show you. So let's focus now on the things that we investigate in this research. The first thing is the hydraulic conditions. So if you have a system and you are always taking, like a pile, and you are always taking the calories, it means that probably the temperature around the pile will increase. So it can be nice if you have a water flow, which will reduce the temperature and will increase the efficiency of your system. So for tunnels, it's the same. And our idea was to investigate the role of the hydraulic conditions. So is the table on the top of the tunnel, at the level of the tunnel, or down of the tunnel? And the idea was to check numerically what will be the difference in terms of hydraulic conditions. Then I will show you. So we began by this condition, and then we have decided, as it is numerical, you know that it's not difficult to tune the parameters. So we have tuned some parameters. I will show you the influence of some key design parameters. And the last thing, it's not a very new work, as it was published probably in 2021, something like that. Probably a lot of people have done better things, but just to show you, we tried to investigate the role of the unsaturated soils in this case. So our case study, I was working, so in the team was a Chinese student, Chen Jingma, and also Alice Didona, who is a professor and was from Italy. So during her PhD, he worked on the Torino Metro Line 1. So it's why we had the case, and our idea was to take the data from this case, to try to model this case, to try to have a good agreement with the data, and then using this good agreement, then to extend by a numerical analysis and to check what will be the influence of the design parameters. So the case is there. So the tunnel is more or less, you see that it's the excavation. So the excavation is there. It's 3 meters 90, so more or less 4 meters. So it's an 8 meters tunnel of diameter. It was made by a TBM, so means that the TBM always excavate a little bit more than the size of the segments. So the size of the excavation is 3 meters 90 for the radius. The interior size of your segments is 3 meters 44 here, and here you have 3 meters 74. So it's not a big diameter. In France, all the Grand Paris Express, the tunnel diameter is 10 meters. This one is a little bit smaller. The soils were made of sand and gravel, so means that it's important by the fact that the permeability of the sand and gravel is not it's high. It's not like in a clay. Yeah, in a clay you can have a groundwater table, but you know that the water flow will be limited by the permeability of your clay. If the permeability of the clay is 10 minus 9, the flow will not be higher than 10 minus 9 meters per second. So it was a good case by the fact that it was sand, so the permeability can be 10 minus 3, 10 minus 2 meters per second. So it means that it was not the soil who was the limiting factor, probably more the flow of the water. The water table was just on the top of the tunnel, and then we had some backfill, but it was not. This zone is not important. You remember that this zone, the temperature will vary, so it's not very important for the geothermal calculations. I will go quickly on the numerical models. We have done, in fact, 3 kinds of models. I will not discuss a little bit, I will not discuss much the first loop model, but we didn't have a lot of experience using COMSOL, and it's not so easy to use COMSOL. So the idea was to try, here it was to reach the long-term properties. Means that when you are working in 1 meter length, we can reproduce all this, and means that for us was just do calculations at long term to obtain the efficiency at long term. I will not deal too much with this one. I will deal a little bit more with the 2 other ones. The second one was used to calibrate on the experimental data. Remember that in the tunnel that we had, the data on the tunnel that we had as two linings, two segments. So we used this one to compare it to the results that we have on the site, and we have done thermo-hydraulic calculations. In fact, in this case, we can assume that you can say that probably it will be better to do thermo-hydraulic mechanical calculations. But here, the settlements, the displacements were not really high, and I'm sure that it's not necessary to obtain the efficiency, the power efficiency. It's not necessary to do a mechanical calculation. The mechanical calculation will be more done by the geotechnical engineer to be sure that it's stable from a mechanical point of view. For the thermal efficiency, what is important is the thermo-hydraulic calculations. We can separate them easily. A lot of people already showed that. And then we have also used a bigger model, 11 loop model, more to check the transient effects on this section. So I will deal more with the 2 loop and the 11 loop. So let's go for the role of the groundwater. So for the role of the groundwater, in all the cases, we should consider what are the mechanisms inside. So we have the concrete and you have the soil. So in the concrete, I wrote it here, we only consider the conductive heat transfer in the lining, and we have considered no convection in the lining. So these 2 mechanisms, the conductive heat transfer is important for the lining, not the convection. For the soil, we have considered the 2 mechanisms. So if we more mechanisms we consider, more parameters you need. Yeah, I will not deal too much with the parameters. The specialist for the how to take the parameters is more Christina. Remember that I'm more a guy from numerical. She gives me the numbers and I can do the calculation. But without her, my calculations will be very bad. Yeah? Remember that. For the water circulation, we have used the Darcy law, and in all these calculations we have considered that the soil was saturated. Yeah? So no unsaturated till for these calculations. What is important to calculate the heat exchange efficiency is the temperature which will go out, the output temperature and the input temperature, and these are parameters from the system. I will not deal too much with them. Okay, so for the calibration we had some experimental, so we had the experimental input temperature, the experimental output temperature, and then we have done some calculations. A guy in Sana and Barla have already done some calculations, and for this first step, our goal was to be able to obtain more or less the same thing. So we reach our goal. You see that here for the heating test, we have more or less the same as the experimental output, and here also. So using this data model, using the mechanisms that I told you, we were able to predict what was measured on the site. Then we have decided, based on this case, by the fact that we have validated our numerical calculations, we have decided to check the influence of the water table position. So means that here you see that it's this parameter, the delta E. So it's the height of the water and the height of the center of the tunnel. So means that we have considered some positive values and some negative values if the water table is down. Yeah. I will show you the values that we have considered. Another parameter which was important for us was the water flow direction. So the tunnel is like that. If we have a water flow like that, probably the effect will not be the same if the water flow is like that or like that. And you know that in the real case, the tunnel pass will not follow the water flow. Yeah, probably I have to go from, I don't know, from one station in Torino to another one, and the tunnel pass is the necessary one to go from point A to point B. It will not follow the groundwater flow. So our idea was to check if what will be the influence of the water flow direction. The other one was the water flow velocity. It's easy to do it numerically. In the field, the water flow is the water flow. You cannot change the water flow. Yeah? Yes, you can stop it. Yeah? If you do some injections or you reduce the permeability, you can stop it. But the idea is not to stop it, it's to increase it. And it's not possible. It's only virtual. Yeah? So it's why I told you, yes, I can change the numbers, yeah, but she will tell me, no, not possible. Okay, these two parameters were part of our study. So I will show you only the results of the 11 loop model. Why? And it's also for this goal that we have done the 11 loop models. If you only do a 2 loop models, you cannot have you will have some boundary effects. Yeah. So it's why we have extended the tunnel to be able to do not have this kind of effects. Here you can see some the effect of the water table position. You remember the delta E? So if so here the 1.45 R means that the water table is upper. So R, it's the radius of the tunnel. So if the delta E is superior to R, means the water table is upper than the top of the tunnel. And if it's negative, means we will not have more or less water table. Okay? Okay. So here, what we can see is the fact that we have an increase if the water table is higher than R. So means that the water table is upper than the top of your segments. Yeah? And you can see a big increase. Here it's the efficiency in watts per square meter, and we can see that yes, most of the case, if you want to have a good efficiency, the water table should be higher than the level of the tunnel. Yeah, so it means that if you have some cases of some parts of the tunnels which are not under the groundwater, probably it's not necessary to insert tubes. Okay. Then the cross angle, and here it's 90 degrees. When it's 90 degrees means that the flow is perpendicular to the tunnel, and you can see that if it's 90 degrees, you have the better Q. Yeah, so means that yes, it's better to have, if you want to have the better efficiency, it's better to have a flow which is perpendicular to your tunnel. The flow will refresh automatically your tunnel. Yeah, like that you will take always more or less always the same temperature around your tunnel. And the last parameter was the water flow velocity. Yes, but it's normal. Bigger is the water flow and bigger is the QS. Yeah, so it's normal, but this parameter is more a numerical one. I cannot change it. I cannot tune it. I can tune it on my computer, but that's all. Okay, using all these results, then we have done some tornado diagrams. We have defined the base case. So the base case was this one. So the direction of the flow was at 45 degrees. So the tunnel is there, the water flow is there, 45 degrees. The velocity was 1 meter per day, and here the delta E was minus the radius. So means more or less no water on the height of the tunnel. We have done this for free. Then we have we have compared to 3 cases, and in all the cases, what we can see for the 11 loop, for delta E equal minus R and delta E equals 0, we can see that the more important parameter is delta E. You see that the diagram is bigger, so it means that it's the first main parameter. The second one is the velocity, and the third one is the direction of the water flow. We have more or less exactly the same conclusion for the delta E equals 0, comparing the base case with this case. And when we use when we have really a water flow which is higher than your tunnel, you can see that we have a variation. We have a change on the ranking of the parameters. The velocity becomes the bigger. Yes, you have water, so you can change. So this one is the bigger, and you can see that finally, the flow direction is not the bigger one. Yeah, the influence is not so big, and we have obtained more or less the same for the 2-loop model. We have done it for the 2-loop model. The idea was to check if finally a smaller model can also be able to reproduce what was obtained in the 11-loop model, which is more rigorous. We didn't have these boundary effects on our model. Okay, so then, so this one was a classical deterministic sensitivity analysis. Then we have done a probabilistic sensitivity analysis of the ground parameters. In this case, it was a little bit more complex. So we have developed a routine using coupling COMSOL with MATLAB. The idea, so in a probabilistic analysis, we should, in the first case, I forget, in this case, we modify a factor by factor. So it means that this factor, when you modify this factor, the two others are constant. In a probabilistic analysis, the idea is more to see what happens when all is moving. Yeah. So it's why we have to define a more complex, in fact, system. And what we obtain is the sensitivity indices for each input parameters. And you can see that, yes, some parameters have a bigger influence, like the variation of the temperature, the water flow density, the water flow velocity. So as for the other, the simpler sensitivity analysis, we have more or less the same parameters. Yeah? With a more complex analysis, we have the variation of the temperature, so it means that it depends a lot on the site you will be, yeah, by the fact that we change the temperature, the input and the output, and the velocity water are the two main parameters using this sensitivity analysis. Last point was the unsaturated soils. So in the Torino case, we didn't have the measurements of the water content versus the relative. We have taken from the literature some curves, and the idea was to try to show what can be the influence of the unsaturated soil. So I have said the questions. If you want, I will not deal too much with that. So here we have considered 3 kinds of soils: a sand, a silt, a claystone. So the soil of Torino was more a sand, yeah. But we extend a little bit more the cases by using two other soils. Be careful, it's an intrinsic permeability. It's not a water permeability. It's why the unity is a square meter. Yeah, it's not only for water. It's a more intrinsic. We had to define we had to define some parameters like the heat carrier fluid velocity, the heat transfer coefficient, the initial ground temperature. So these parameters were defined as constants, and we have defined some loads for thermal loads for each layer. So the temperature is here. So we set a period where all is off, means that we have no change of temperature. Then an on phase with the heating mode, we stop the process, and a cooling phase. Means that we have done several steps just to see what was the influence with time on the system. So we have measured the temperature like they used to do around the tunnel, and you can see that Here, it's the change in temperature versus the distance. You can see, yes, that when you are very close, you have a very high change of temperature. And another thing with this one, so this shows that the difference of temperature. The change in degree of saturation was not so big. You can see that the higher one is 0.03 to 0.07. And it depends a lot on the time you are doing your calculations. Means we have done 1 year, 5 years, 10 years. And you can see that the change in the degree of saturation is not really big using unsaturated soils. And the other result was we checked the initial degree of saturation. We took 0.2, 0.5, and 0.8. You see that with 0.8, we have more or less no influence with the time. We have a bigger influence with 0.5 and a bigger with 0.2. So the main parameter which is important in this study was the initial degree of saturation. So we should know with a good accuracy what is the initial degree of saturation to be able to see the change in this degree of saturation with time. Then we also had to introduce the matrix suction, the effective degree of saturation versus the matrix suction. Same remark. We took the curves from the literature. Yeah, it's not. Yes, it's real curves, but it's more curves for the literature. So we use this curve. So as we had sand, silt, and claystone, so we use the sand, the silt, and the claystone. So you see that we have a different matrix suction depending on the soil. So it's classical curves that you can find on the literature review. And here, here we have down the saturated zone. Here, in the upper part, the unsaturated zone. Sorry. And you can see that when you have a delta E equal to R, the changes that we have on the saturation. It's a variation of the saturation. You can see that for the sand, yes, we have a bigger variation of this saturation than for clays. It means that it will take much more time due to the fact that the permeability is lower. So it will take much more time to have a big variation of this parameter of the initial vertical saturation. Same for so this was the result for the tunnel top. For the tunnel bottom, we have more or less the same result. So I will go ahead. Then here we can see also what happens in the sand, in the silt, and in the claystone. You can see that yes, we have much more variations on the sand. It's also the permeability. We'll introduce that, yeah, like for the same. For the other ones, we didn't have a big difference between the silt and the claystone, but for the sand, you see that the colors are lighter around the tunnel, so it means that we have much more difference. Then we have calculated the thermal power, and the thermal power is not so different. In fact, it was for us. It was strange by the fact that here we have a big difference, but for the thermal power, the difference is not so big between sand and claystone for delta E equal to R. The difference is more or less the same. It's lower for delta E equal minus R for the heating mode, and we had more or less the same result for the cooling mode. So it means that using the unsaturated parameters, we didn't find a lot of variations in terms of thermal power. Now, the conclusions. So I tried to show you that the water table is the most important thing. I don't know what are the rules here in France. When you have to do this kind of tunnel, you should know at least the level, the groundwater level. You should set some piezometers at least 1 year before the beginning of your work. Like that, you will know it's very important by the fact that during the year you will have cycles and you will change also your efficiency. In my calculations, I didn't take the cycles. I just take a constant level. Yeah, so it means that it will also influence, in fact, your system, this water level. And in France, we have much more levels. We have you have also the, I don't know how to say, if you have a flow, a water flood, you can have a bigger level. Yeah, but the water flood is an accident. It's not something which will stay a long time. So it's not the one which should be used for the design of this kind of structures. Then I show you that when the water table is higher than the tunnel top, the water flow velocity is the most sensitive, and it's not always the case. Be careful. If the water table is down, it's the water table which is the most important parameter. Otherwise, the temperature difference between the pipe inlet and the soil is the most sensitive parameter. So means that, yes, it's better to go deeper. Yeah, like that you will have probably more difference than being too shallow. For the unsaturated part, I showed you that the relatively low initial saturation corresponds to a greater accumulated change, but the difference is not so important. A dry assumption can only be applied when the water table is above the tunnel. It will not change the results. And the natural convection has a small impact on the thermal power, but has a great impact on the temperature distribution in the coarse soil. This conclusion, I just said it, I didn't illustrate it, but it's in the thesis, so in the PhD thesis. So if you're interested, we have done some calculations to consider the convection or not and show what is the difference. And that's all for today. Thanks a lot.
Merci, Daniel. Thank you.
Donc
Obrigada.
comme je suis très fatigué, je vous propose de faire les questions en français.
A língua natural do Daniel é francês. Se alguém se arrisca...
Então, vocês podem fazer as perguntas em português.
Daniel, pode sentar também.
Mas o meu problema é que o meu vocabulário não é um vocabulário técnico.
O vocabulário dele é português.
O mais complexo para mim é de ir buscar as palavras técnicas.
Não, aqui a gente tem colegas que Mohammed and Pankaj are from India and Ghana. They only speak English.
Yeah, so for respect for them, in my mind you should speak all of you. No, I'm joking.
But the others, we can translate. You can respond in English or or in Portuguese.
Let's do the best.
Here is a salad, Brazilian. French. E Daniel, obrigado, né? Para a gente, você falou do efeito dos ciclos do water table, né? Em solos não saturados, a gente tem aqui os ciclos do grau de saturação, que varia também, né?
Ok.
E isso para modelar...
Varia de certeza mais do que...
Teria mais incerteza, né? Okay. Então, para variar os ciclos de grau de saturação numericamente, isso seria possível.
Sim.
Também, né? Fazer ciclos...
Quer dizer que é uma rotina a mais, mas pode ser tomada em conta. Se vocês têm uma ideia do ciclo durante o ano, pode-se tomar em conta no modelo numérico.
A gente tem que varia, a gente tem estações secas, estações úmidas, e tem uma condição intermediária, né? Então tem essa sazonalidade. E também do water table, né? Isso tudo no console, né? Eu fiz uma pergunta só de curiosidade, mas eu vou deixar as questões em inglês.
Isso tudo pode ser introduzido.
Vou aqui para o André, nosso professor aqui do Departamento de Estruturas. Tem outro microfone. Desculpa. Eu troco o microfone? Tá. O microfone para questões eu já liguei, André.
Hello, Daniel. Nice having you back here in Brazil. All of these thermal analysis that you did from a distance, and considering that I forgot to bring my glasses, you had a radial symmetry. Is that so? Do you have a radial symmetry there that you could use in the numerical analysis? Because this simplifies the problem a lot.
This one are not radial, but yes, we can, yeah. But probably we can have our first step could be that. But here, we wanted, in fact, you remember that our case, the tunnel case, was the Torino case, and the tubes were, they were perpendicular, so we wanted to simulate the distribution of the tubes. So it's why we decided to do a 3D model. But I agree, yeah. If we simplify the geometry of the tubes, yes, we can do an axisymmetric calculation, more or less.
Yes.
Yeah, sure. And it can reduce a lot the time calculation, yeah. I agree. But you know, our student was.
I have some students that is studying the effect of the groundwater table, so I think he has a question.
And another thing that we didn't consider is the fact that you know that the permeability in the soil, it's not isotropic, yeah. So if I will do the kind of calculation that Andre is talking about, I will lose some information. You know that in most of the granular soils, due to gravity, the permeability in this direction is smaller than in the other direction. Yeah? And another thing, if you want to do some mechanical calculations, you know that you have the coefficient at rest, and in a granular material, the coefficient at rest is not equal to 1. Yeah? It's 1 minus sinus of the friction angle, so it's not isotropic. Yeah? So it's why in most of the cases in geotechnics, it will be difficult to consider an axisymmetric calculation. Sorry.
I think Letícia can question in Portuguese, in French, in English. How
do as you.
He was in France 6 months, so.
Chinese can be also. I'm joking.
Thank you for the presentation, Daniel. I'd like to ask about the effect of the groundwater flow on downstream structures. For example, if you have piles or other structures downstream the flow, if you had modeled this kind of problem, for example?
No, the time calculation was not so small, but in all the cases you will have a shadow effect. Yeah, so means that you have some. If you consider one pile, yes, it's like an isolated pile. But if you have 2 or 3 piles and the flow is in this direction, be sure that one of the piles will, the thermal efficiency will not be the same. So yeah, it's important. If you have the idea is in the future, if you want to install this kind of geothermal structures and you have, I don't know, some parking, some piles, yes, you should consider all the environment to be able to define the thermal efficiency. Yeah, but in the time calculations were heavy, so we didn't go in this direction. But it's a good, yeah, it's a good idea. Yeah.
Thank you.
So you speak English very well, better than me. So next time I will assist to your one of your presentations.
Have other English students here? Maybe a question. Other Brazilian students.
I need a question from Africa and one from India. So.
So Mohammed, did we work with unsaturated soil?
I don't want to set pressure on you, but.
He's very, Daniel is our friend. So
thank you so much. So
from which country are you? From which country are you?
Ghana.
Ghana, okay.
Yes.
Oh yeah, you told me, I forget.
So I would like to know if you considered the flow of air within the tunnel.
The air flow?
Yes.
No.
Airflow.
No.
But I believe that should have some serious effect.
Yes, it can have a serious effect inside the tunnel, yeah, sure. Some people have considered, you can find in the literature some people who only have considered the airflow. But the fact it's not so easy with this software to consider the air and the water. Yeah?
Within the tunnel.
Yeah. But it's important in a tunnel, the airflow inside the tunnel, yes, can modify the temperature condition, yeah? Here, in fact, we indirectly take into consideration this. Mohamed, we indirectly take into consideration this by the fact that we know the input and the output temperatures. Yeah, so we directly insert them, and we didn't consider the airflow. But yes, sure that it's better to consider the airflow.
Okay.
Yeah, it's another limit. Thanks. So Africa succeeds, you know? Let's try to see if India is able to.
Hello, good afternoon, Professor.
Thanks.
I am Pankaj. So this topic is very new to me. Actually, no one in India is working on geothermal energy.
You should, you are a lot.
So I hope, I hope in future. But there are multiple ponds in India, some region of Himalaya that used to give a hot spring are there. So people are trying to work in that area, but that is very much, how can I say, rocky
Okay.
strata is that. So can we do such operation in that kind of strata? I am new to this topic. I don't know, but I'm just asking the strata is very intact, and from that strata hot springs are coming. If you search in internet, it's the reason Manikarn.
Okay.
Manikarn reason, that's
If you have hot water,
I have
if you have hot water,
if you have
hot water at shallow temperature, means that yes, you will have
you
a.
can see the video.
Okay.
This is the
Is it
place. Yeah, it's the reason in Himalaya. So
Okay.
so
Okay,
this
we're
is a
sure
rocky
that
strata.
If you have a big difference of temperature, you will increase your thermal efficiency. Yeah, the thermal power that you will be able to bring will be higher.
Okay.
So yes, sure that you can.
Okay.
But the main, in fact, in most of the cases, the bigger difficulty is the fact that in most of the cases, in Europe, we have to build the structures for by the fact that we need the structures. Yeah.
Okay.
So it's the additional cost to add the tubes is not so big. In your case, probably you will have to build a structure only to take. Yeah. So probably
for example, we when it comes to the foundation, we have a helical piles and the system to
yeah, but the problem of
extract the energy. So how we
helical
can-
piles, you
Yeah.
have to set the tubes.
Yeah.
Where will you
My
set?
question is how we can install a foundation like this that we can extract energy from a rocky strata, which is rocks are very big, not that the upper layer is of rocks. It's
So I will
My question is,
re-say what
how
I
we can
said.
execute
First, when you are in rocks, I'm not sure that you need to do pile foundations, as the rock is always probably stronger than the pile. Yeah, the Young modulus of a rock, if it's an intact rock, you can have more than 40 GPa.
Okay.
Your concrete, when we usually do a design, we took 20 GPa. So I'm not sure that you will need to create these piles for foundations, as your rock is already strong. Yeah.
Yes.
So it means that you will induce an overcost by the fact you will have to drill to set your tubes to take the thermal. Yeah, it's possible, but it's not like the structures I was talking about. The structures I was talking about, we need them.
Okay.
So it's just an extra cost to set the tubes. In your case, can be probably the thermal efficiency will be higher, but you will have to create a structure. And then also the other question, here you have close to the mountains, will you have a lot of people which will beneficiate from this energy or not? Yeah. Remember that. One of the big problems in Europe is we should have somebody which will use this energy. Yeah.
Okay.
Close, not so far. Yeah.
Okay. Thank you.
Claro. A gente tem chat no YouTube.
Professor, we have two questions here from the chat,
Okay.
YouTube chat. I will try to translate for you, okay?
Okay. You can say them in Portuguese, and then if I don't
Okay.
understand.
The first one is in English.
Okay.
Oscar, the student, the Christina's student. If I could see.
Yeah.
Okay. Yeah, that's a problem. First of all, thank you for the presentation,
a question,
Professor
thanks.
Daniel. Regarding the understanding soil model, was soil suction taken into account in the model? And what is the impact on the results?
In fact, we took 3 kind of soils: sand, lime, I don't remember, and clay stone. And we, using curves from the literature review, the idea was to check what was the difference. So we have a difference on the initial saturation and the modification of the soil saturation with time. And for the thermal power, the difference was not so big. But probably it's also due to the fact that the parameters that we took are from the literature. So I'm never sure, in fact, as it is not real site. The only real site that I had was the Torino one. The two others are, yeah, so I'm not sure of my results, in fact. Yeah.
And the other one is in Portuguese. It's a little bit better for me, right? Ele falou que a empresa que fica responsável pela administração da estação é diferente da que constrói. Há algum caso em que o sistema foi montado e não utilizado?
Houve aquele caso do Grand Paris, que eles fizeram os tubos, mas foram obrigados de os preencherem. Porque as pessoas que faziam o controle, eles não aceitaram.
Ah, verdade, porque você disse que acho que os fiscais não tinham experiência, isso,
nem
né?
quiseram.
Maluco isso, né? Okay, just two questions.
Okay.
Thank you.
Thanks.
More questions from people from here, né? Português, não tem problema que o Daniel fala, né?
Yeah, the girls seem not to be really active, yeah?
Olá, parabéns pela sua apresentação. Não é da minha área, mas é uma curiosidade. Existe diferença de temperatura que vocês conseguem, enfim, coletar do solo em diferentes solos ou diferentes rochas? Por exemplo, alguma dá uma temperatura mais alta, outra mais baixa, algo nesse sentido?
Só tomar o exemplo não sei como é que o rapaz chama, mas naquela montanha Himalaia, você vai ter uma temperatura que é muito mais elevada. Mas depende também assim, ele já tem água quente que vem. De certeza que vai ser muito mais eficiente. Mas, para mim, o estudo tem de ser feito na zona onde você quer instalar o sistema. Porque a eficiência só pode ser caracterizada no sítio. É a mesma coisa quando você tem de fazer uma estrutura e verificar a estabilidade da estrutura. Você vai fazer ensaios no sítio da estrutura. Okay? Tem de ser feito da mesma maneira. Porque pode ter um incidente geológico, pode ter várias coisas que vão modificar o sistema. Um lugar é um lugar. O problema é que tudo a geologia já assim não foi o humano que fez, a natureza. Quer dizer que pode ter não sei se você tem experiência, mas quando você faz um furo aqui e um furo aqui, com 50 metros de distância, você já tem. Eu tenho uma experiência sobre eu vou falar inglês porque eu estou cansado. So I had an experience on a project about rigid inclusions. Rigid inclusions, it's like a kind of pile, yeah. And the idea we wanted, in fact, to do a case just with the slab, with no piles, and the case with the piles and the slab, yeah. And the idea was to set some instruments to bring the data and compare them. And the only site that we found was close to a river, yeah. And at the end, we found that without piles, we had less settlements than with piles. Is it normal? And the distance was 20 meters, yeah? So it's why I say be careful. We should do your investigation close to the site where you want to install the system. Yeah? It's very important in geotechnics. It's very important. And when a company has to do the works, I don't know how it works here in France, but in Brazil, in France, it's organized like that. You have a I don't know how to say, but we have the G0. The G0 is the primary geotechnical investigation. Then you have the G1, the G2, and the G2 Pro. The G2 Pro is the phase where you do the design. Yeah. So till there, from the G0 to the G2 Pro, it's a design company who will work. And then, so you know that the design company, they will do more or less the investigation. They will do not a bad investigation, but they don't know exactly, till the G2, they don't know exactly where the structure will be set. Yeah? In the G3 will be done by the company who is working and doing the structure. This company, to optimize, they can redo some boreholes, yeah, to be sure that the geology is It's not changing. And sometimes they will discover problems. Yeah? And then we have the G4. The G4 is the control of the people who is doing the works. And then we have the G5, and the G5, it's when you have a problem. When you have a problem, we do a G5 just to better understand what happens on the site. And if there is a big problem, we can redo the G1, the G2 to find a new solution. Yeah? But it's the idea of geotechnics in France. We have the NFP, so Norme Française, so it's a French standard, NFP 94500, which the main goal of this standard is to improve the knowledge of the site with the G0, G1, G2 increasing with the increase. Yeah? So it's why we should do the investigations on the site where. Yeah?
Daniel, have some. I don't know if you have other question. I have just a question because I saw that you put some risk analysis in your presentation. So you consider the parameter as handle variables.
Yeah.
In this case,
Yeah.
I didn't because you passed it very.
Yeah, I
quickly,
passed very fast.
So
yeah.
just for you can connect the console with a MATLAB as the program that Professor Beck doing. You can connect console and.
Yeah, but Andre has, in fact, Andre has developed all the routines to do the analysis. He can connect them with the software you want, the software you need. Yeah.
You can put the parameter as handle variables, and it's interesting.
The worst thing is the fact that you have to do a reliability analysis. You will always have to do a lot of analysis.
Okay.
Yeah? So if your numerical calculation for one calculation is heavy,
yes,
yeah, it will be
because it's very be very heavy.
Depending on the number of simulations you have to do for your reliability analysis. Yeah. So it's why we have done our sensitivity analysis on the 2 loops. Okay, on the 11 loops, probably the student will continue to work until now. Yeah?
There are many months of work.
Yeah.
Okay, no, thank you.
Yeah, but you show that you should be connected. Yeah. Reliability can be used for all the problems for geotechnics, but not only for mechanics, for electricity.
You have many data of geothermal piles. We have data results that you can simulate using console, and we can, for example, estimate the variability of the efficiency or something like that using. Okay, I'm speaking English. It's funny. Alguém quer more questions?
When she's with me, she always told me, please speak French with me.
Became crazy, Portuguese, French, and bad English. Kevin is my undergraduate student.
Okay.
And he started to work on geothermal wall.
Okay.
My question will not be as profound as theirs, because I haven't finished my graduation.
You are still welcome.
Yes. I wanted to know cost-wise if the cost of the geothermal energy could solve the problem of, in European countries, energy tends to be more expensive than here in Brazil. Do you think that the geothermal energy could be the solution to that?
Can be the solution, I don't know, but can be a piece of the solution. Yeah? If you have, for a news, as I told you, a tunnel, it's more than 1 kilometer long. Sure that it will bring a lot of energy to the cities, and probably will be able to reduce the number of nuclear power plants that we have in France, yeah? For sure. But in my mind, we should have a mix between different kind of, like in France, we have dams. In my mind, dams are very important. But some countries cannot have dams, so probably they can go more to geothermal, as all the people has geothermal energy. Yeah? It's a hard question. Not profound, but hard. I have also, there is, you remember, Christina, you have the PhD thesis of Yvon de la Rabelais?
Si.
Yeah, you have it. Yeah? Can be interesting for you.
Yes, the Yvon.
Yeah, probably it's in French, but.
Yeah, but I think he communicates something in English.
Not much.
Not much. I have a thesis in French.
But good for France, it's a good one. I don't know. Probably in the world they have done more.
I have this. Can pass to him.
It's a good one for
yes, energy walls.
retaining walls.
Okay, and now André have one more.
One more question. I feel disappointed with the fact that, let's start like this. In Brazil, we have a lot of problem with the refrigeration, right? We always need to cool our buildings. And we all know that in order to have a fresh building, you need to, for instance, make openings in both sides to get the air through, and maybe avoid having a window to facing the sun. So these obvious things that we do to keep a room fresh. Well, people who basically build up and then they put an air conditioning because it's easier. Developers, they make a square building. They want to sell apartments in all sides, so they don't care about it. They just plug in an air conditioning.
In my
afterwards.
mind, it's a very bad solution.
I know. This is my complaint. So, but it's the easy solution. So this is my point. Do you see a future where thermal energy is so easy to install that it will become the easy solution? Instead of people just plugging air conditioning with dual cycles so they can warm up and cool down
You
whatever
know that
they feel like. They pay the energy bill then later. Nobody cares also. Nobody cares with the emissions.
In
Nobody
fact, in
cares
Europe,
with
you have the
anything.
evolution. I have done a lecture. I don't know. I could do it also, but you have an evolution of the regulation. Means that in France now, I have some buildings I want to rent, but you have a class, an energy class, and I know that A, it's a better, B, C, D, and if I have some apartments with level G, next year I will not be able to rent them. So I will have to do something for energy. Yeah. So the government can imply, but in France the government says you will not be able to rent, but I will help you to improve the level of your buildings, and it's a good way. For geothermal energy, you can see probably in Switzerland it's a good case. Most of the buildings they are creating now have geothermal piles. Yeah, and if you have the piles which are connected to your building, you know that it's perfect. The building, you are the owner of the building, you are the owner of the piles. You didn't have to exchange energy with other buildings, so it's perfect. Yeah, we just have to. Probably the government could play a very important role on the system.
Yeah, it's very popular in Switzerland.
Yeah, in Switzerland it's amazing. All the buildings from the companies they have to do geothermal piles. Probably also Lalui, the professor Lalui is he was in Paris, and I remember that he was saying that it's very important. What is the cost of setting a tube in a pile? More or less nothing compared to the price of the structure. Yeah, and I remember he was in the meeting, and the people from the Grand Paris Express were close to me and say, yeah, but they cannot. Yeah, they cannot.
In this conference in 2019, we were together.
Yeah, you were there.
I did a presentation, showed the case of 6, and the Lalui is the man that started this in Switzerland, né, na Suíça. A pessoa que começou lá no aeroporto da Suíça com energy piles e tal. And I asked him, what do you think about Brazil? Because in Brazil you need much more reject heat in the soil than extract, né? Maybe it's the unbalanced system. He said, Christina, just put the pipes inside the pile.
Yeah.
If you don't use, no problem, because it's very cheap.
The cost is nothing, in fact, compared
no
to
cost. So please try. Let's try. He said he's a...
And Christina says, I will try.
So I put the pipes and then place the piles, the walls.
And she shows that they will do a building in the University of São Paulo. Let's set the pipes.
He's very, he said that you should try. Huh?
In fact, in France, I was talking also with Christina about the problem of inserting the monopiles. But the problem is the fact that the engineers, the geotechnical engineers, are very conservative. They don't want to change. If they have a rule who is okay, they don't want to change. And it's like that, in fact. Yeah?
The problem is geotechnical.
No, not only. Probably not only, but part of. Yeah? It's why probably if we are waiting for, if I want to answer to your question, if we are waiting for the geotechnical engineer, we will wait for decennies. Yeah? If it's the government who says, oh, you should, it will be faster, for sure. The geotechnical engineer will not, he will have to apply the rules. Yeah?
Another question is a philosophical question.
Right.
Yeah, maybe another engineer school, no, like structure, technical, the new things, the risk, this is something good. Okay, Leandro?
But we have one more question
Let's
for
go.
you in the YouTube
Which
chat.
language?
In Portuguese.
Oh, no.
Parabéns pela palestra, professor Daniel Dias. Nos sistemas geotérmicos implantados em túneis, o fluido que circula no sistema é o mesmo que o aplicado em fundações por estacas ou valas? E qual é o fluido? É o João Manuel Filho. Manda um abraço meu para o professor.
Pode mandar também um abraço para o João. Sim, sim, é o mesmo que a estaca, já. Não sei como é que é um fluido calor.
Fluido, é que no inverno lá tem problema de congelar.
Ah, pois. Não, mas.
Descongelante aqui na Europa.
É um fluido um pouco diferente. Vai ser um fluido um pouco diferente na Europa que aqui. Pois, aqui pode ser água. Mas em França ou em Suíça o problema vai ser mais o gelo. Como num carro. Sim, para limpar os vidros, a gente em França temos um para o verão e temos um para o inverno. Aqui vocês só têm o verão. Bom. Porque se a temperatura estiver menos 10 e eu vou com o verão, aquilo fica tudo gelado, ainda fica pior do que o que estava no início. Mas a ideia é só um líquido que vai poder transferir, sim, vai poder trazer as calorias da... Não é nada de muito importante. Ok?
Tá tão cansado, tantas perguntas, nem imaginava, né? Porque chegou de viagem hoje, né? Mas mesmo assim, queria mais alguma coisa.
Mas penso que ficou melhor que o que eu pensava.
Mas o Daniel vai estar aqui com a gente até terça-feira de tarde, né? Vai embora na quarta. E vai estar com a gente na Geotecnia, se quiser questões, né? Mesmo todo mundo aqui, né?
Se quiserem, depois eu vou para o laboratório, não sei aonde.
Agora
eu vou ficar, mas se quiserem vir falar,
né?
eu vou estar disponível.
Tem a disponibilidade. Hoje ele está um pouco mais cansado, mas é só dar uma caipirinha que já melhora, Daniel, não é?
A caipirinha?
A caipirinha ele vai cair duro.
E agora ainda estou a 90, mas caipirinha...
Toda banca que eu chamo o Daniel online, ele fala, e a caipirinha? Né?
Era só para brincar.
Para brincar, é brincadeira. Nossa, dá para isso no YouTube. Corta depois.
Não fui eu que falei de caipirinha.
Brincadeira. Corta lá, né? Gente, então eu vou agradecer muito o professor Daniel.
Obrigado.
Thank you very much. Merci beaucoup. Pela apresentação e por tudo, por esclarecer as dúvidas e participar, né, desse evento aqui, apoiar a gente aqui na nossa pós-graduação, dar essa oportunidade aos alunos de pós-graduação e de graduação também aqui, né?
You know that I like to be in Brazil, so it's also a pleasure for me.
It's a pleasure for you. Can you speak English or Portuguese? You can do both, né? Muito obrigada, Daniel.
Obrigado.
Corta aí, pelo amor de Deus.